Go to my website. Did you find the little link that says R? It's very teeny. But I'm not a web developer, so. All right. PC. Okay, it'll take a minute. Oh, interesting. All right, now let's see if I can switch back and forth between my laptop and this screen here. That's what I would need to be able to do. Let me pause Integrity for. All right, we're having technical difficulties, so we can't see my laptop, but we're working on that. So let's get started. This is the second part of the Introduction to R course. The first part we had a few weeks ago, and then my daughter got sick, and anyway. So now this is the second part. And this part, we're just going to focus on doing some analyses, just doing some fun things in R. I think it'll be enjoyable. Now, I know Iven's name. Is it, do you pronounce the W like a V? Like Even or Iwen?
Actually, this is Even.
Even?
Yeah.
Is it like a V or a W? V? So Even?
Even.
Okay.
Yeah.
And I've forgotten your name.
Gojun.
Hmm?
Gojun.
Gojun?
Yeah.
Okay. And your name?
Lu.
Lou?
Yeah.
Oh, so nice and easy. You have to have mercy on me. If it was in Spanish, I could pronounce it, and if it was in English and maybe German, but that's it. Any other language, and I'm totally confused. Yeah. Lou is so nice. I already told you my only joke from Chinese, right? I told you my only joke from when the girls tried to teach me Chinese. That's the only joke I have. So, oh, you're a genius. What happened? Genius people fixed it.
Yep.
Okay.
Like it's working.
All right. Excellent. All right, no more technical problems. Maybe I'll edit this out if I ever have a chance. So anyway, they had names like, they just chose American names to tell their American friends, so they were like Francis and Michelle. I think that were their names. I was like, really? You're from Taiwan and your name is Michelle? Yes. So, all right, let's move on here, and I'll take out my inappropriate jokes as we go along. So this is what we did last time. We didn't really get to basic analyses last time, although there's some information in the PowerPoints. And then this is what I plan on doing this time. Well, I'll have to change this. Do you have any problems that you had? Has anybody tried to use R and run into problems, or you have questions before we get started? No? Okay, well, let's just keep going then. So, wait, do I have the wrong... I think I have the wrong presentation up. Hang on. I'm really going to have to edit this a lot. Oh, yes, I do have the wrong presentation up. Sorry about that. My bad. Okay, no, seriously, we're going to... Okay, no, starting for real this time. So part 2. So last time, we did some general information about R and how to do some basic things, and we didn't do very much in the way of analyses. This time, I just want to do mostly analyses, some graphs and some analyses, some exploratory analyses with visuals, because I really like visual exploration with R. I think that's something that the modern world offers us. I had teachers who used to say, don't show me a graph, show me a table. A good table is better than a graph, and I don't understand this, because graphs make perfect sense to me. A good graph is a wonderful thing. So we're going to do some graphing and then some analysis. That's basically what we're going to do. So if you guys have downloaded that file, try starting up RStudio. I thought we would use RStudio today. It's not the only way to interact with R. There are many ways to interact with R. RStudio is what's called an integrated development environment. It does lots of neat things. It doesn't replace R. It just sort of wraps around R. So you communicate with RStudio, and RStudio then communicates with R. It's fairly transparent and easy to use. I mostly just use it for the text editor. There is also a good text editor in R, but just because I'm really familiar with RStudio, I figure let's start RStudio. So have you guys got RStudio started? Okay, some of the ways. So if you just started R, then shut down R and then start RStudio. Hello, we're just getting started. So shut down R and start RStudio. There are two things that I want to focus on first. And the first one is just starting RStudio and setting the working directory. So I actually can't remember which pull-down menu it is. So do you know where you saved this text file? So this text file, did you save it on your desktop or something?
Yes.
Okay, so save it. If it's saved somewhere, let's find that. Oh, it's right there. Okay. Okay. So do you want to make I recommend making a folder or something for today. Make a folder on your desktop or on a flash drive or something and put that text file in it. So you can go back to your desktop and drag and drop that text file into a new folder. You might call it like Intro to R2 or something like that. So find where you put the text file. Oh, you don't have to do that. It's already saved. I'll show you what it's doing. Just go ahead and close this. It is saved. So right-click on your desktop and just right-click on the desktop itself and choose New Folder. So New and then Folder. And give it some sort of name, like for today. Okay, and then just drag that and put it in there. Okay, now from within RStudio, so go back to RStudio, and I cannot remember where this is. So you might as well just maximize RStudio, make it cover your whole window because it's all you really need. So don't open file yet. Don't do that. There's an easier thing you can do. So let's just maximize RStudio. So, well, I was going to say, yeah, there we go. Just hit that. And so from within RStudio, type in RST. Oh, maybe you don't have RStudio. Okay, try and go back to all.
Install RStudio before you use it. It's not easier.
Oh, it's not installed.
It's not here, but I go to your website and download RStudio.
Oh, I thought it was installed on all these computers. Oh, I'm sorry. So did you guys have to install RStudio from a website also? Okay, the website is rstudio.org. All right, I'm going to proceed, and then I'll come back and help you again when we have a place to stop. So go to the World Wide Web and go to RStudio when it wakes up. rstudio.org. And then you can download RStudio and install it. I didn't know. I'm sorry. IT told me RStudio was installed here, so my bad. All right. So those of you that have RStudio running, let's see where it is. Maybe Tools? No, Session. Click the Session pull-down menu and see where it says Set Working Directory. Click that and choose Directory. Now, find the directory where you put your file. So the desktop, probably. I think that's in computer. Desktop is hard to find. Computer. Just a minute. Desktop is so hard to find. Here, let me try. I think look what this is. Users. And this is, one of these is you, right? Mesh? That's you? There we go. Desktop. Okay. Okay, and then now that you've got that, select folder. Now, once you've selected the correct folder, then one of your panes will show files, plots, packages, help. So you have 4 different panes. Yes, this one. And this one right here.
This one?
Yeah. Just click it. Have you installed software before? Yeah, you can click Run. If that doesn't work, then just try to save it. So if you click on Files, now you should see the file that you downloaded if you selected the working directory. See, so you see it right there. Intro to r.txt. And if you click on that, it will open it up in here, which you already did. So if you click on that file, now you have all the syntax available to you. Is it busy downloading? Oh, okay, there we go. All right, so once you're in RStudio, let me just switch over here. I've rearranged my RStudio. Now I'm going to, once you have RStudio started, you can just take your RData file, which is the workspace, and you can just say open with RStudio. It's kind of nice. So I'm going to open RStudio, and my RStudio will look different from yours because I've customized mine. So you have lots of different things that can happen in the different panes and in the different 4 places. And you can put them wherever you want. So I go into Tools and Options, and here, Pane Layout. You can choose 1, 2, 3, 4. You can choose what you want. I like to have my source on the left and my console on the right. So source means that's where the text files are going to be. And console, that's where the R is going to happen. That's the main R window. So I don't like them up above each other. I like them left and right. But that's just me. You can arrange them however you want. You can also, under Appearance, you can choose fun colors. So this one is Tomorrow Night Bright. There's a different one, much more bright. I'll choose that one, and that one's a more, wow, that's kind of a crazy looking one there. Okay. Anyway, you can customize it any way you want. But you need to know the two windows that I use the most, and these little buttons, you can maximize a window. So the 2 windows I use the most are the one here that has your files in it, that shows you all your syntax, and then the console, and this is R. Now you can click here and type your commands into console, 2 + 2, or you can type them over here. Here, let me create a new file. You can have lots of files open. You can have 2 + 2, oops. And then you can send that to the console with making sure the cursor is here on this line. You can do Control-Enter. And then over here on the console, you see that the answer appeared. So I like to type here and just hit a lot of Control-Enter to send it over. Now, if I have a lot of things, I can select them all and hit Control-Enter, and then they all happen all at once. So Control-Enter is very nice. And then this is always being saved. Everything over here on this side is in a text file, and you can save that text file. So you can say File, Save As, and it will try and save it in your working directory, and I can call it temp.r. And so now I have saved that. Thanks, Lou. There we go. Okay, so have you downloaded the file from my website yet? Because that will make, you got that? Okay. So the challenge right now is from within RStudio, open that file. And most people are there, but we're waiting for 1 or 2 people still. Oops. I forget how small the screen is when it's in the projector. You can't have widescreen. Okay, so the first thing to do is where it says Session. Click there, and down where it says Set Working Directory. So we want to tell it where to look for files and where to save files. Click Choose Directory. And now, go find where you put the file that you downloaded, the text file. Oh, you didn't download a text file from my website. Okay, well, just create a new folder here in my documents, a new folder, and just call it Intro to R or something so that you can put things there. It's not creating a new folder. Okay, it was creating them and not showing them to you. Just something so you'll remember that it's for this course. And then just, oops, you need to hit Enter. Oh, no, there you go. Okay, so now you need to go to my website. Which is that, darren@lrogers.com. So, just my big long name. Oh, here. DARRINLROG, no space. ROGERS.com. Okay, and click up here where it says R. Just click on that. And then right-click here. Now go back. Do a right-click and save as, or save link, save target as. And then save that in Documents, in the folder you just created. So Documents, no, not a new folder. Go to Documents, in Introduction. Double-click and save it there. Awesome. All right, now you're done with the web. So you can close the browser if you want, or minimize it or something. Well, it doesn't want to show you anything because it doesn't recognize .r. Just go back to RStudio now. Oh, sorry. Double-click that. I'm sorry. This is the Choose Working Directory. Click Select Folder. Sorry. So now this is the working directory, and it's showing you the file you just downloaded. So you can click on it, and it will open there, and that's the R console there. All right, so we're just going to work from within RStudio today, if you guys are okay with that. If you know how to do this without RStudio, go ahead. It's not hard if you know what you're doing. But if you're new to this, you might want to do things from within RStudio. So we set the working directory so that when we click Files, it shows us the files. I have more than you guys do because I've been developing files here. It'll show you the history of your commands. That's kind of nice, so you can go back and do things that you did previously. When you create a graph, it'll show up in one of these windows. And like I said, you can customize it to tell it where to show you the plots. It'll show you which packages are loaded. That's going to take a while. There's a lot of loaded and installed packages. And then the workspace will show you all your objects. Now, I have a lot of objects because I've been working on this class. You probably don't have very many, or you have none. When you type something in the console with a question mark, for help, like if you don't remember how the plot function works, you can just do $plot. And then over here in one of these panes, you will see the help function appear. And it's actually connecting to the internet, I believe, most of the time. And so you can get the help function there. So, and you can rearrange things to make them bigger, smaller, etc. So I'm going to work from this text file right here. Now, has everybody gotten to this point where they have the text file open? Okay. So my recommendation is you do things from the text file and do Control-Enter to send them to R. So if you click on this line that downloads the support data set from my website, Control-Enter, there. Now you have the support data set, and you can say list, and you will see sup, which is the object that was created by that command. So any of these lines, hit Control-Enter, and they will be sent to R. So fool around with that if you feel like it. And I'm going to go back very briefly here. We're not going to go very far. Oops. What happened? Oh, I touched the screen. So anytime you're doing anything in R, I recommend you work from the script window. You create a new script file. You can just do new R script if you're doing something new. And then save it. Save as, and save it in your working directory. And that way you're always saved. And if your computer crashes or R freezes, which it does sometimes, as I've discovered, then you always have what you were working on. You never lose your work. It's nice. And Control-Enter is what sends the commands to the console. So we'll be doing that today. Just in the script window, Control-Enter, and then seeing what happens. And then you can, of course, do things yourself. Sometimes if I'm doing things I don't feel like saving, I just want to check what 2 times 12 is, I'll just click over to the console window and type right in there. And that's exactly like working in R. But usually I want to save my commands in case I want to go change something, or I type something wrong, or I want to make a big complicated command or something like that. So Control-Enter from the script window is very nice. So the file for today, which I think everybody has, you downloaded that. Start RStudio, change your working directory to wherever you put the file. And then from within RStudio, you click the Files pane and click on the file, and it opens it. It's very nice. So setting the working directory is really nice. In R, there's a command to do it, but RStudio, there's just a pull-down click, which is nice, so you don't have to remember the command, and you don't have to type a big, long path. C:/Windows/ oh, so that it's a little faster to do that in RStudio to set your working directory. All right, so let's play a little bit. Let's play a little bit with exploring data. some things to do are easy to do in R. So let's do a histogram in the support data of parental socioeconomic status, which is annual income. Now, before you do this, you need to get the data. So switching back over here, you'll need to run this line right here. So just put your cursor anywhere on the line and do Control-Enter. And that will download from my website that spreadsheet, that CSV file, and it will create an object named sup, and it will put it in your workspace. So just click on that line, Control-Enter, and you will have the support data loaded in. So it's at the very top. Scroll to the very, 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 very top. There we go. So yeah, just if I were, I'd maximize RStudio because then you can see all the lines without breaking. Okay, so just click anywhere on that line. The cursor has to be on the line. Either that or you have to select it and then Control-Enter. You can select the whole thing or you can just put the cursor on the line. So if the cursor's on the line, so Control-Enter. No, Control, hold down Control, and then press Enter. That's, oh, you named it .m somehow. I'm not sure how that happened. So it's confused. So it doesn't think it's an R file. Okay, let's go back and rename it. You've got MATLAB? Okay, I don't know what to do with MATLAB. So there was a problem. Yes, we noticed that. So it was in your documents, right? Introduction. And I don't know how it got named .m. Did that file somehow get named .m? Was that just on this computer? Here, I think we need to see the extensions. So this is a problem with Windows. It doesn't like to show you important things. So let's see, how do we, folder options, properties? No, we need folder options. How do we get folder options? Does anybody remember how to do folder options to force Windows to show you extensions? Because the problem we have here is that this, actually we can do this. Let's try this. Let's just try that. So now there should be two of them. This is named .m and that one's named .r. So let's get rid of that. Oh, it thought it was .m, so it thought it was MATLAB. And so when you clicked on it, it opened MATLAB.
But we click the same thing, it has two.
What?
I mean, first I click here, right? But it is not R. But just now you click it again and it is R.
Oh, I did not know this. Okay, so now you're here and you look in Files. Wait, why is it not showing you the files? Session, set working directory, choose directory, introduction. Okay, there we go. So there we go. Now see how it's all colored nicely? So now if you do Control-Enter, it sent it down there, and it's contacting the internet.
I can just click anywhere.
Anywhere. You either click on one line and it will send one line with Control-Enter, or you can select a large range and it will send the entire range. All right, so just moving down here, all the commands we're going to do today are listed here. So if you want to see all those, the names, the variable names of this data frame that you have imported, because what you imported is a matrix. You can do names of sup. You could type that in yourself, but I've already typed it so it's easier. And you can see there are a lot of variables. But don't worry, I just want to do something with a few of them today. So lots of variables. And if you want to see what type all the variables are, you can use this function str, which means structure. So show me the structure of this data frame. And so it shows you what type they all are: integer, integer, numeric, integer, integer, factor, and it shows you the levels. It shows you the different values. So this is a nice way to see what kind of data you have. It's nifty. But I like view a lot because that's just like a spreadsheet. So if you do Control-Enter and view sup, then I see it down here. It's showing me a new window. And this window is a strange-looking window because my color scheme is very weird. So this is just like Excel or SPSS or something like that. So this shows you all of the data. NA means blank. NA is what R uses to represent no answer. Blank. So you can look at all the data here. You can see the names, although you can barely read them because of my terrible color scheme. I think you guys probably have better color schemes. So if you want to just look and see what the data are, then you can just choose View with a capital V. But that's only something you can do from within RStudio. It's a special RStudio function. If you don't want to use View, you can use Edit. EDIT sup. And that will do the same thing. They're slightly different. View has a couple of advantages, but it's not much of a difference. So you can see all the answers here. So there we go. People's jobs. That's kind of neat. So, and you'll notice Edit prints everything out on the screen when you're done. That's kind of weird. I don't know why it does that, but it does. So now that you can see everything and you know what's there, let's explore some things. One of those variables, so if I do names again, and I did a capital S and a lowercase UP for my data frame name. If I do the names again, if I scroll up here, one of these down here is SES MOFA year. Anyway, so we asked people how much money their father made and how much money their mother made last year, and then we combined those two things together to get an estimate of the household income. These are college students. So this is from a study I did with 450 or so UTPA students a few years back. So this is their income. So once you've got this in here, getting a histogram is very easy. You just use the hist function. Now, I don't know if you remember, but when you're trying to access some data inside a data frame, then you need to, and you want to access one variable, you need to do the data frame name $, variable name. And that says, look in this data frame at this variable. So in this case, it will be sup, $, and then SES MOFA year. Now, capitalization is important, and I know I've done some crazy things with capitalization on the variable names here, so just try and just hit Control-Enter or whatever. So if I hit Control-Enter here, I will have a histogram of that. So it popped up a new window, and it showed me a nice histogram. There we go. And you can see up here in this histogram that it's positively skewed, as income always is. So most people have these lower values, and then some people have ridiculously high values. So this is 1 million. So this is one person who reported that their parents' combined income last year was $1 million. But most people are down here $10, $20, $30, $40,000 a year. So it's a very horribly skewed distribution. So getting a histogram is really easy. You just type in hist and that. Is everybody able to do that? Just get the histogram? And then we're able to see which window it pops up in. So you don't have to type it. You can just go down there and click on that line, Control-Enter. Oh. Object sup not found. Oh, it's, here, try escape to stop whatever it's doing. So I think you did that when it was in the middle of thinking of something. You do have this data frame. Plots? No. That's very strange. Is it giving you any error messages? I'm going to recommend we just shut this down and start it again. Don't save anything. And we'll just start over. Because I think it's behaving. So, save nothing. Let's kill it. Let's see if Windows can kill it off. Your R was, we had R freezing up over here, or RStudio. So we had a bit of a problem there. It's really frozen, isn't it? Okay, there we go. No. All right, now let's try again. So no space, just RST. There we go. Then it will find the correct program. Go through the same process again of selecting the working directory from session once it's going. Oh, did it remember? Oh. Yeah, introduction. And then select folder. Okay. So you need to download the data again because we got rid of that. So do that line again, Control Enter. Okay, that looks correct. And now, yeah, now go down and see if you can do the histogram line. There you go. All right, so I think everybody's able to get a histogram now. The point of this is to show you that making a histogram is easy, and in R, I find it very easy to transform things because that's not very useful histogram. But this might be, if I transform it by taking the base 10 log of every value, this might be very useful. So the way you do this, it's still histogram, you see here, it's still histogram of something, but it's not histogram of just the values. It's histogram of log 10 of the values. So log 10 is the function that takes the log of the values. Of course, you have to make sure that there are no zeros in there. If you were worried that there were zeros, you could always just do +1, like add 1 to all the values first. Anyway, you can do Control Enter there. I don't think you need to. I think there are no zeros. I think I tested it. And now this is much easier to see. You can see the variability here. So you can see that there were some people down here who reported in the hundreds. This is base 10, right? This is log 10. So down here there were people who reported below the hundreds, and these are the people in the thousands and the 10,000s and the 100,000s, and then one person up here in the millions. So it's much easier, and you get a nice, it's not really normal, but it's not nearly as badly skewed as the previous one. And we do that sometimes when we're analyzing data. We want to transform it. So some things are very easy to do in R compared to other programs. Not everything, of course. So if you transform it, then you still do a histogram of something, but then the thing you do a histogram of is just the log transformed version. Oh, I put log here. That will do a natural log. But in this text file, it says log 10, which will do base 10 log. And that's all I know about logs. I'm not a math guy. So some things are a little less straightforward. So before we go on, I think I'd like to talk right now a little bit about indexing. I'll try and make this as painless as possible, and then we'll just get on with doing fun analyses. Oh my goodness, it's almost been an hour because I took so long to fix technical problems. So in R, there are lots and lots of objects that look simple in your workspace. If you do ls parentheses, or if you just click on the workspace pane in RStudio, you'll see, oh, I have this thing named X. And it looks so simple. But if you look into it, it actually has lots of little pieces. It's made up of pieces. So a matrix and a data frame are very similar. They're just a big square matrix, right? A data frame's like, you can think of it for now as a special kind of a matrix that's good for holding data with variable names and things. So we use brackets right after the name of the object to refer to the smaller parts of the object within it. So if you have a vector and you have one dimension, you would just do a bracket and put one number in it. So if you typed in this vector, and there's code to do this in your text file. So if you create a vector named v, you say, make me something named v. And what you should put in that, so assign, is combine 10, 20, 30, 40, 50. So that will create a little vector named v, and it'll just have 5 values in it. So I create this vector here named v. Let me maximize this because I don't need the plots right now. So I create this vector named v. I'm going to switch over here and just type the name of the vector. There we go. That's all it is. It's just these 5 values right here. If I want to just look at the fourth one, I can do v bracket 4. Now the 4 isn't a value, it's an index. It says go count up to the fourth one. Just show me the fourth one. So if I do that, it shows me 40 because 1, 2, 3, 4. The fourth one was 40. Now with data frames, it gets a little bit more confusing because there are 2 dimensions to a data frame. A data frame is a 2-dimensional matrix, kind of like that support data is a very large 2-dimensional matrix. So let's make a smaller one. This command here, capital D, lowercase f, that's just what I choose to call it. You don't have to do it that way if you want. I'm going to choose this function, data.frame. It creates a data frame. And what I want to create the data frame out of is these 4 values, 1, 2, 3, 4, and these 4 values, 5, 10, 15, 20. Now, when you're creating a data frame, you can give it the names. You can say the name of my first variable is this, and it should have these values. The name of my second variable should have these values. So if you do Control-Enter, now I have the data frame. And if I type the name of the data frame, it'll just show it to me. So there we go. I created a little data set, a teeny, silly, pointless data set. It has one variable that has these values and another variable that has these values. If this was traditional data, then this would be participant 1, and this would be participant 2, and 3, and 4. Are you wanting to participate as well? Oh, okay. So anyway, so it has those values. And so you can refer to those values using these brackets. And the way it works is you type the name of the object. So this object is named capital D, lowercase f, df. This data frame is. Now this is not part of it. R will automatically show you the row numbers. So there are ways to refer to the row numbers, but that's not what we're going to do here. This isn't data. This is just an accident of R showing you the information. So you can type in the name of any row and the name of any column. It's always row, comma, column. And you can have spaces before or after or between. It doesn't matter. Sometimes people like to put spaces there. R doesn't care, as long as you have a bracket after the name of the object and a row and a comma and a column. So this is how we can refer to just little pieces within a data frame. Actually, it's the second way. We already know how to use the $ in variable name as well. So if I type df bracket 4 comma 2, it shows me 20 because it goes down to row 4, 1, 2, 3, 4, and column 2. It shows me 20. So row 4, column 2. Now there are some little tricks, like if you leave one of those spaces blank, it shows you everything that refers to. So if I say df row 4 comma and I don't type anything there, it'll show me the entire row 4. So that's like saying row 4, all the columns. Column 1, column 2. There's only 2 columns. And if I just want to see the entire second column, I can do the same thing. I can say df nothing, comma 2. Now notice it doesn't show it as a column, because when you do this, it kind of strips it out of whatever. It's like it makes it naked, yanks it out of its clothes, and gives it to you all naked. It just turns it into a vector, just turns it into a list of numbers or a list of values. Now, as you know, there's a different way that you can get the second column with a data frame, and that's just using the name of the variable, right? You can say df $var2, and that'll give you the same thing. So data frames, there are 2 ways to look at columns, 2 ways to ask for the columns, and 1 way to ask for the rows. I'm going to switch back to this for a second. So here are these examples. With a matrix or a data frame that has 2 dimensions, you put the name of the object and then the row number or numbers and the column number or numbers. And if you leave them blank, you get everything, all the rows or all the columns. So here's the example from the syntax file. And then we can do weird things. So this is where it gets really interesting. You can put an expression for the rows or the columns. I can put, with quotation marks, double or single quotes, the name of a variable as a column if I want to. And that's kind of a nice flexible way to do things. Or I could just put the number 2 here because variable 2 is column 2. And then this first part, df $, etc., I can say only show me the rows where variable 1, where the value that's in variable 1 on that row is greater than 5. So you can put expressions in there that are very, very nice and powerful, and I'll show you a way that we can use those to split up your data a little bit. So that, that command running here, df, okay, data frame, and then in the brackets, only the stuff where variable 1 is, oh, I changed it. Greater than 5 wouldn't work because I don't think there is a 5 there. Yeah, it would give me an error. I said greater than 2 here. And then variable 2. Notice I used double quotes. It doesn't matter. They could be single or double. And it showed me 15 and 20. So I want to see only the stuff that's in this column, so variable 2, but only the rows where this value is greater than 2. No, not that one, not that one. Yes, this is greater than 2, but I'm not want to look. I already said I'm not looking at this column. I'm looking at this column. So this is greater than 2, so show me this. This is greater than 2, so show me this. So 15, 20. So this is the little piece that I pulled out of there with that little command. And that's a quick and fast way. It can take some thought and lots of trial and error when you're trying to do something a little bit complicated, but it's very powerful. It can allow you to do very powerful, complicated things with just a few lines of code sometimes, or sometimes just with a simple little command. Are there any questions so far? So, yes, absolutely. Yeah, expressions? Sure. Yeah, you can put big, complicated expressions in both. There's no limit to the amount of expressions you can put in there. Okay, well, let's create something a little larger.
Let's do just exactly the same command that we did that time. Change that parentheses R2 to
Let's put this up so it's a little higher so you guys can see it a little easier. By the way, you remember the up arrow? It just shows you, it goes back through your commands. So greater than 2, and you could say variable, and you could say command df $. Now you'll notice it, even though you're putting it in an index for this object, it doesn't know that what you're referring to in here refers to this object. Does that make sense? You still have to type in df $. You can't just say variable 1 is greater than 2, because it will say, what is this variable 1 you're talking about? I'm looking in your workspace, and there's no object named variable 1. And that's a great annoyance when you do this every once in a while. But then you realize you can do crazy things, like you can have one matrix over here and another matrix over here. And you can say, show me these rows over here that have the same row number as something that I'm telling you about this matrix over here. So even if you didn't understand that, it makes it more complicated, but it makes it to do simple things, but it makes it possible to do very powerful things. So you still have to tell it df $ variable 1, or you could say df bracket, comma, 1, close bracket. You could use indexing in there too. You still have to tell it where to look for these values. It doesn't know automatically. So even though you're already talking about df, it doesn't know you're talking about df. You have to tell it. So what was the expression you were thinking, Will?
R2 is less than 20.
Because that doesn't exist, right? Oh, wait. Wait, that should work.
Well, see, that's what I was trying to understand at this moment. When you put, I couldn't understand why, in your first example, it wasn't telling us the information in that first column. But when you put a condition.
Oh, it says, wait. It says undefined column selected. So I did something wrong in telling. Oh, you know what I did wrong? This is not a column thing. I'm giving it 2 rules for rows. They need to both go before the comma. I'm telling it 2 rules for the rows. I'm not telling it a different rule for the column. So this will work. And so, oops, not N. So this is a special operator. It means and. Oops. df $ variable 2 is less than 20, and only show me the stuff that's in variable 2. There we go. That's the confusion I had here. Because your idea, you want to select rows based on these two criteria, but the only column is still this. So this is only criteria for choosing columns, and it doesn't make sense to choose columns based on something that's in a row. So this is which columns to choose. And if you say variable 2 is less than 20, that's not a row, or that's not a column. That's something in one column. That's a subset of one column. So that's not a column itself. So that doesn't make sense to talk about there. So it said undefined columns. All right, I get tripped up by that so much. All right, so let's move on a little bit. So let's do a histogram with a little bit of indexing here. Let's get some new data. The punishment attitudes data, which we worked with last time. I'm just going to do Control-Enter and have that download. I'm going to do a quick names of that object and make sure, there we go. Make sure I got it. Okay, how lost is everybody? Are you guys able to follow along? That digression that Dr. Watkins and I had.
I'm crazy. I've done RStudio 5 times already. Installed it, I had a fatal error.
Oh. Is this trying to install RStudio?
Yeah, I downloaded from here.
Oh. I mean, you're installing it?
Yeah. I have it fine. If you click on over here, so you download another one. So that's the first time. This is the second time. I know you right now you're downloading another time.
Is R running?
Oh no, I closed
Oh.
it.
Huh. I do not know.
I'm sorry, what?
Maybe reading the download.
Oh, really? It's in my computer already? Well, no, I did in. No, this is in my office computer.
Oh, office.
It's not here. Yeah, I'm remotely into my office computer.
So you did this already, right?
Yeah, I did this already.
Okay.
It won't show. Actually, you know what? I don't want to cancel.
So it is installed.
It is installed.
Okay.
Before I install another time, see, it is here.
RStudio. Oh, we're using XP?
Yes.
Okay. I didn't know these were XP. I thought they were
And
Windows
it will
7.
give you the data. I will try.
Is that the wrong version of RStudio then? Was there a different one for XP to download?
I think it was Windows XP, Vista,
Oh,
and
okay.
7.
That's what I thought. Okay. Well, I'll pause again in a minute, but let's.
Another question while we're kind of sorting this out. The file that you created and you downloaded from your site,
Which one? The matrix with the data in it, or just the syntax file? The code file.
I only downloaded one so far.
Oh, well, every time you do the Control-Enter, read CSV, we're getting a file from my site as well. So.
Okay.
Uh,
So this file with the dot little r
mhm.
extension on it,
Yes.
that can only be read in RStudio.
No, it's just, actually it can be read nicely by R's script editor, I think. Anyway, it's, the .r is, when R gets installed in Windows at least, .r or .R is reserved to refer to R-related programs. And so the .r, the only reason I name it that is because RStudio will then recognize this as an R syntax file instead of just a regular text file, because it's just a text file with a .r on it. And then it will do the syntax highlighting and that kind of thing, and it'll work within RStudio. But I believe it will work with other things. I can open it with Notepad++, for instance, and do the same thing. You can open it with Notepad by just doing right-click, open with Notepad. All of these things work. So it's just a flat text file. You just change the extensions so that RStudio and I think R will recognize that it's special and do some fun things with it, like syntax highlighting.
If I was going to read it into R by itself,
Mm-hmm.
probably
I don't do that much. I think you'd use the source command. So source and then specify its. So it wouldn't be nice because I haven't written it to be a beginning to end script, but it would just run everything. It would just run every command in order. that's in there if you were to read it in, but it should work just fine. I think. That's not something I do very much. When I get online, I feel like I should do scripting more, but I don't. All right, is everybody ready to move on a little bit? Okay, so let me do my slow switching here again. So in the punishment attitudes data frame, we asked people's attitudes about punishment and such like towards some hypothetical, some imaginary people who had committed a crime. They just saw a little story in their survey. This person committed this crime, etc. So we asked them, we gave them a questionnaire that had several questions that were about how accountable or responsible the person who committed the crime was for their behavior. So how accountable is this person for their behavior? How responsible are they? So we can look that variable, act.all. We actually we showed them a sex offender and a non-sex offender, but act.all is combining their answers for the sex and the non-sex offender. So accountability.all. So you can do a histogram of that, as long as you've got the punishment data set read in, punishment $accountability.all, act.all. Now, we can also do just the undergraduates. In this study, there were 3 groups of people included. There were 2 kinds of treatment professionals. They were from these organizations called ATSA and APA. And then there were undergraduates. So there's a variable called trt.pro, and the only answers are y or n. So there's a variable in. Let me just switch here so I can try and show you what this is doing here. So if let's say view pun. Let's see if I can find this. I can barely read this. Okay, so this you can't even see this because of my terrible color scheme, which I've never managed to fix, or I'll never bother to fix. This is whether each person is a treatment professional or not. So this is their subject group, undergraduate student. Those are not treatment professionals. And then when you get down past many hundreds of them, you get into APA, American Psychological Association, and Association for the Treatment of Sex Abuser Therapists. They are treatment professionals. So the group can be divided in 2, treatment professionals and non-treatment professionals using this variable, treatment.pro, yes or no. So if we go here, we can do just a quick histogram of everybody's accountability ratings all together. It's relatively normal looking. It's beautiful. Or we can do something different. Instead of doing a histogram of just this variable, we can do a histogram of this variable and do some indexing. Now, it's going to be just one item in the indexing because this already just pulls out one long list of numbers. This by itself is not a data frame. This is just a vector of numbers, just each person's accountability rating. So it just took that one long column, and that's all we're looking at. And so to index that, you just need one value, one thing. So I'm going to say just pick the ones of here where right next to it, that other variable, treatment professional, is equal to, and you have to use 2 equal signs because this is like a computer sciencey kind of programming language thing, is equal to no, or n, in quotation marks, single or double quotation marks. And then I put a color for the histogram. I put comma and then I did a color just so that there's a pretty color for it. So if you do that, you'll see a histogram of just the undergraduates. Oh, you notice it shifted a little further to the right now, and it gave it a crazy name up there. And if you ever want to just see the graph nicely, you can click zoom, and you can get a bigger version. That's kind of nice, I think. And if you ever want to save it, you can choose export, and you can choose to save it as a PNG or a JPEG or a GIF or something. You can also copy it to your clipboard so you can paste it into a Word document or something like that. Anyway, we're not going to do that right now unless you feel like it. But anyway, this is just the undergraduates. Now, I made those green because there's another trick. Let's do another histogram here. And you'll notice it's exactly the same. This line so far up to here, these 2 lines are the same. It's just that now treatment professional equals Y, yes. So now let's see a histogram of just the treatment professionals who are indicated by treatment.pro equals Y. And now this line, this continues. There's a comma. This command is not done. I wrapped it around. And there's a color. This is an HTML color code. You don't need to know these, but you can add an extra 2 numbers at the end of that color code to make it a little bit transparent, which is a cheap trick I did. And then histogram, you can do add equals true, which means add this new histogram right on top of the old histogram. So that's kind of nice. So I'm going to select this whole thing, and then I'm going to hit Control-Enter. There we go. Now we have 2 histograms on top of each other. We see the histogram of the non-treatment professionals' ratings of accountability, and then the green one underneath it of the treatment professionals, and the green one underneath it of the non-professionals, the students. And you can see that the students were more likely to believe that the criminal had accountability for his actions, and the therapists were less likely to believe that. It's not the most beautiful graph in the world. I could definitely make it easier to use. But it does show you that with some quick little tricks and some indexing, you can create subsets, graphs or analyses for subsets of your data. Any questions on this? Were you able to do this with the Control-Enter and make it all happen? So if you, just to review, if you put your cursor on any line and do Control-Enter, then it sends that line. And also, if you select anything and do Control-Enter, it'll send the entire selection over to the R console and run it. Alrighty. Now we can also do bar charts. I'm not even going to go back to PowerPoint right now because I think this is pretty self-explanatory. But let's just scroll down here. Bar charts are nice when you have a categorical variable and you're just counting frequencies, just counting the number of people who this or the number of people who did that or the number of observations in this category or that category. So for bar charts, you have to do an extra little step. You have to create a table. And then you have to do a chart of the table. Because as it turns out, the bar chart function, it isn't very good. There are other functions you can get that are not included with base R. There are lots of packages you can download that will do bar charts like this for you. But in the base R, just the stuff that comes with the initial download, you have to create a table first. Luckily, that's very easy. So right here, I created a table and I called it polit.table. And you just use the table function. And so let's make a table of this variable, participant political affiliation. It's a really long name. Now I wrapped everything in parentheses so that I can see the table as well as create an object. So if I don't include those parentheses, so I'm going to select, I'm going to select everything but those parentheses and just send it, then it'll create the table, but it won't show it to me. Whereas if I wrap everything in parentheses, it will both create the table and show me the table. So you can see the table right here. Now what this table was, this variable was asking people, what's your political affiliation? Do you see yourself as more liberal or more conservative? So I chose to, in this study, make this is like really liberal, and this is kind of liberal, and this is middle, and this is kind of conservative, and this is really conservative. So this is the distribution of liberal conservative. So now that we have that table, now that we have this object named polit.table, and you can look in your workspace and see that it's down here. There's a section, polit.table. I created it. Now that I have that object, now I can make a bar plot of it. And I'm going to do something else first, because -1 and 1 and 0 and 1 and 2, those don't really help me understand what's going on. So I'm going to create a little vector of names. So you can see there are 5 names here: far left, left wing, centrist, right wing, and far right. So I'm going to create that little variable. I'm going to call it polit names. And I'm going to rename that table. So the names function tells you what the names of a one-dimensional object are. And polit table is just a one-dimensional object. It's just this and this and this and this and this. And these are the names. I want to change those names into something more useful before I make my graph. So I'm going to, if you just type in these, just the names, so I'm going to just select that and hit Control-Enter. These are the names of the table. But I want to change them. I want to replace them with these political table names that I created. So I'm going to do that, change the names into those names. Now if I do political table, well, it had to wrap around because my screen is so small. But now it makes more sense. Now I actually understand the data. It's kind of nice. Maybe this was an extra complication, but and now, if I want to, I can just do bar plot. So I could, just right now, I could do bar plot of polit table. There, it'll give me a nice bar plot. I can zoom in on it. There we go. That's a neat bar plot. But I wanted to be more fancy. I wanted some colors. So I created another vector with just the names of some colors. And I happen to know that I looked up online what names R understands for colors. So I looked up these colors on an R website that says R color names. So I created this other vector, which is polit col. So if I type that in, polit colors, that's what it is. So it's just a list of 5 words, 5 character strings. And those happen to be the names of colors that R understands. So now I can do bar plot of the table, and then color equals, and that's a common way to say colors in tables, color equals these colors. So now it's prettier. Okay, not super pretty, but prettier than gray, I think. I'm a little obsessed with color, though. People have to kind of calm me down and say, too much color, you're going crazy. So you may not want to do the same thing. All right, was anybody stuck on any step of what we did or don't understand what happened?
My graph's over here. I'm trying. How do I like the arrange. How do you
Zoom.
Oh, you zoom it. No.
So that just
the
shows you
window.
preview.
See, here's over here. But my
Oh,
cursor's
okay.
Over here. What do you
Tools, options.
Yes.
Yeah, I like it in the upper right. And then pane layout. And so you can choose what you want. So this is this pane, this pane, this pane, this pane. So you can choose what you want. So just choose different things. I always choose it so that my text files are on the left, source is on the left, and console is on the right, and my graphs are on the upper right. That's my favorite way to do it.
Got you.
Oh, that's beautiful. I can't hear you. I'm sorry.
Oh, I cannot give it that view again. This one?
Okay. Okay, so that's the table. So go up here. So try that bar plot, the table. Control Enter. Okay. And then if you've created all of these, yeah, try that. There you go. Is anybody else having any difficulties getting this to happen on your computer? Are you stuck or are you doing something else? It's just because it doesn't have enough space. So drag this and drag this bar. There you go. That'll do it. It just does. Yeah, if you don't see the names underneath, RStudio makes decisions where it says, oh, if there's not enough room for the name, I'm not going to show you. And you can adjust the size of the text, font, and everything, but I didn't want to get into that. So you can always just do zoom, and it'll show you in big. And that's actually why I chose these short names. It should probably be very liberal, somewhat liberal, neither liberal nor conservative, very conservative, somewhat conservative, but they were too long. They kept disappearing. So I made short names just for this class so we could see them. Oops. Legends, yes. We'll do some legends in a minute. And there are some functions in R that make making legends fairly simple. And there are other graphic programs that will do a lot of this more quickly and more beautifully for you. My favorite is called ggplot2. But I didn't want to get into that. You have to learn kind of a different way of thinking about graphs to do that. It's really awesome, but it might not be your favorite thing to do. So now what if we want to do a two-way bar chart? Well, we have to do a two-way table, and that's actually easy. Table, if you do table and then one list of values, it'll make a frequency table of just whatever's in that list, like a vector. If you do and it can be a character vector or number vector, it doesn't matter. If you do one list and another list, it'll make a two-way table of that. And you can make three-way and four-way and 10-way tables, even though it's like impossible to understand them. But you can do as many variables as you want within the same data set, and it will create all those tables for you. So we can make a two-way table easily, just the same way we did before. I'm going to say polit table 2 is table of punishment data set, participant political affiliation, and punishment data set subject group. So I want to look at what the political affiliation of each person is by the subject group they came from. So these are the undergraduate students. That's Association for the Treatment of Sex Abusers, and that's American Psychological Association therapists in private practice. So these are their values, and if I put political affiliation second, then this would be transposed. So depending on which one you do first, that's going to determine which is the rows and which is the columns. But I can create a table just like that, just a two-way frequency table. Crosstabs, you can do chi-square easily on this. Actually, I can do chi-square very easily on this. So I can just do chi-square test of polit table 2. There we go. Uh-oh, the chi-squared approximation may be incorrect. I believe because I have very low frequency counts right there. But yeah, very, very strongly rejected null hypothesis if I'm okay with that low frequency count right there and maybe right there. So yes, political affiliation does depend on the subject group that you're a part of. But that's not what I was interested in. I was interested in making a bar graph. So I still have those polit names, right? So I can change the, now I don't want to change just the names. Once you have a table that's a matrix, if you just say names of this, it'll say, what are you talking about? R will say, this doesn't have names. What it does have is row names and column names. So it has, where are we up here? Row names. That's a special function, row names. So it'll show you the row names of political table. But I want to change those to be the names I created before, far left, left wing, etc. So I'm going to do the same thing I did before, but I'm going to change the row names now. And now if I look at that table, now I've given it new names, new row names. I could change these too by changing call names, COL names instead of row names. Those are two separate functions. But I just wanted those to do what we did before, but now I have to do it with row names instead of names. And now, you know, if I do a bar plot of this, polit.table2, I'll get a bar plot. But I looked at this, and this isn't the bar plot I wanted. It gives me a stacked bar plot by default, which might be okay. But maybe I didn't really want this. Maybe I want 5 columns with, you know, far left and left wing and center and stuff like that. Well, that's easy to do. I just transpose the table. And the transpose function is one of the simpler functions in R. It's just T. Oh, sorry, I'm getting ahead of myself. So let's go back. Let's just make a bar plot of this. There we go. So this was kind of a nice one. I sort of like it. You can kind of get an idea of the distribution of right wing, left wing, centrist in each of these groups, APA therapists. It also gives you an idea of the size of the group. So this is a small group. There's only 100 and some odd. This is larger, and this is very large. So that's one way to do it. And we can add a legend to it. Once your plot is created, you can just add things to it. You don't have to create a new plot. You can just start adding many, many things to it. So there's a function called legend, and you can tell it where to put the legend, which is this little thing, and what to put in the legend. Well, I want the row names in that legend. Because remember, the row names are far left and left wing and center, and that's the values inside these bars. That's what I want. And then fill is the colors, so I want those colors I created before. So that looks really hideous, but let's zoom. Oh man, this is horrible. What have I done? This was working so nicely before. Obviously, I'll have to adjust the size of the legend. That didn't work very well. Oh man, that was horrible. I wonder what happens if I start from this a different size of graph. There we go. That looks a little more normal. That's more what I was going for. So RStudio, this is one of the things I dislike about RStudio. It puts all your plots in that little space. If it doesn't have enough space, it says not enough room to show you the plot. And it rearranges the sizes of the elements of the plot so that they fit. And R doesn't do that as much. If you're just working from R without RStudio, then it doesn't do that with your plots. You can do it a little by dragging the window around. But anyway, so you don't have to know how to make legends or anything like that. I just thought it might be a nice thing to look at. So see, it's getting crazy as I resize here. If I want to transpose the table and do a different kind of a bar plot, then first of all, I'm going to need 3 colors instead of 5. So I'm going to create a new vector of colors. I'm going to call it color 2. And now instead of doing a bar plot of political table 2, I'm going to do a bar plot of the transpose of political table 2. T just means transpose. So it'll just transpose it, just flip. And I'm going to use this, beside equals true. And that is a bar plot thing that says instead of doing a stacked bar plot, do a side-by-side grouped bar plot. And there are going to be groups, and each group is going to have 3 bars in it. And I want the 3 bars to be different colors. I think that's what I'm going on. Anyway, I created this color group here of 3 different colors. And I'm going to use that. That's polit color 2. And I'm going to use that as the coloring for this new bar plot. So I'll do Control-Enter for this one. There we go. And I actually like this one more. I don't know. They're both nice. But if you look at the greens, you can see, oh, did I have a legend that I made for this one? Yes, there is. Although we have that same problem again. I wonder if I just make this bigger. Like I said, this is one of my few frustrations with RStudio. I love it most of the time, but sometimes it's a little weird. Right, so this is a kind of a useful plot, I think. So the undergrads, you can see that they are like that, and then the ATSA group, you can see that it's like that, and then the APA, you can see that this is their political affiliation. I don't know. Either one works. You can decide which one you like more. Okay, we have about a half an hour left. Now I can keep doing more graphics, or we can skip to doing some analyses like t-tests and ANOVA and regression. Which would you prefer to do? Some more graphs or some analyses? Analyses? Anybody else analyses? Okay, so there's more graphs in this syntax file, and you can just read through the syntax file and run them, and I think that'll be fun. But let's skip ahead to some analyses here. Let me go back to mosaic plots, box plots, scatter plots, correlograms. All right, so let's go to some analysis. T-tests, very easy. We can try an independent and a paired samples t-test. And I'll show you that they're fairly simple. The way you set up your data for a t-test can be one of 2 different ways. So, for instance, you could have variable 1, 1, 5, 3, 2. You could just have an object named variable 1 and an object named variable 2. And then you can do t.test variable 1 comma variable 2, and that'll do it. That'll do an independent samples t-test on them. But it's more common to have your data set up like in a data frame. It's more common to have, the values and the group. 1, 2, 5, 3, 8, 9, 12, 0, 1. And then group A, B, A, B, B, A, B. This is the more common way to set things up. And then you use a different mechanism to do many, many things. T-test, analysis of variance, regression, a lot of charts. And that's the formula interface where you will do this. You will do t-test tilde group So it's this by this. Values by group. And you'll get used to this interface after a little while. This one, the original one, t-test, group 1, comma, group 2, that's easier to think of, but it doesn't work well with the way data are always set up. So data are almost always set up like this. One row each participant, and then the variables are in columns. And so for t-tests and analysis of variance and regression, we use this formula interface in R as a quick way to get some of these analyses done. So let's skip. Yes. Yeah, you can think of it as the dependent variable and the independent variable. You can think of it as response, predictor. And in fact, in regression, you will use something like this. You'll just use the LM function, and you'll have your y variable, x1 plus x2 plus x3, ... as many x's as you have. So it's called the formula interface, I think, because it looks like a regression formula. And actually, this is how we enter regression analyses. It's very much like a regression formula. I like it because it kind of, the way I conceptualize regression after going through these classes in grad school is like this. So anyway, let's get back to t-tests. So here's this question. Do treatment professionals attribute less accountability to sex offenders than non-treatment professionals do? So do the therapists attribute less accountability than the students? And we saw the two overlapping histograms, and it looks like there's a difference. So t-test, and you can see that this is the dependent variable. This is the measured variable. Punishment, $, the punishment data set. Accountability for sex offenders by the grouping variable, which is punishment, $, treatment professional. So just to remind you, this is what that data set looks like. So this is the treatment professional. It's just yes and no, Y and N. And then over here somewhere we have, there we go, punishment.so. So these are scores from a questionnaire. These are some scores from a psychometric questionnaire asking how much people thought the person, I'm looking for accountability. This one, accountability for sex offenders. How much accountability the sex offenders had. So that's what we're dealing with here. This is a measured quasi-interval level variable, and this is a categorical variable that only has 2 possible levels. Now, if R encounters more than 2 levels in this variable, you'll get an error, and it'll say, what are you doing? There's more. This is a t-test. You can only have 2 things. And then you can use indexing if you want to say, okay, just the ones that are this or this. But this is a nice example because there's only 2 values for this variable, treatment professional or non-treatment professional. So the default for the t-test function is to do an independent samples t-test with a 2-tailed hypothesis test. And there we go. There are many alternatives, and then people online will always tell you, write your own function. So this has some odd choices that are very different from SPSS's choices for how to do the t-test. I've looked up some of these things, but I'm not familiar with all of the terms that are used there. But online, people assure me this is a very reasonable way to do independent samples t-tests, as long as your assumptions are met. So it shows you the data. It shows you the t-value, degrees of freedom. This will sometimes be a non-whole number, because it does some corrections if it senses different variability between the groups and hugely different sample sizes, for instance. I don't know all the conditions, but it will correct your degrees of freedom as a method of trying to make your t-values and your p-values more accurate. But it's nice that it turned out to be a whole number here. And it shows you the p-value, which is very small, 1.035 times 10 to the negative 13th power. So yes, that's less than 0.05 for sure. Now, it tells you the alternative hypothesis. True difference of means is not equal to 0, so you can see that's a 2-tailed hypothesis test. And it gives you the confidence interval for the difference between means. And then it shows you the means. Group not a treatment professional, N, the mean is 3.45 for accountability. And yes, treatment professional, it's 2.95. So It's fairly simple. It's got all the stuff that you need to plug in. If you want to see how things look, you can always do a box plot. So you could, I can just copy this, and the box plot function will take that formula interface as well. So I can just copy that, except instead of saying this, I can say box plot. And I can just do Control-Enter there. There we go. And I have a nice box plot showing me the two medians being different. That's really nice. It's a quick way to see if things are going on. But yeah, the t-test, it's a fairly simple process. The hard part is understanding this formula interface. But as soon as you understand that, it makes more sense. And in fact, SPSS wants this as well. It doesn't use the same terminology, but it wants one variable that has your dependent variable in it, and it wants one column or variable in your data set that has the grouping factors in it. So, sorry.
That follows exactly order, like, the dependent variable is y equals a function of x.
Yeah, y is a function of x. Yeah, I think that's why they created that formula that way. And there are a lot of functions, both graphic and analysis functions, that use that formula interface. I like it because it makes sense. It keeps things consistent. That's how we think about response variables and predictor variables. And in fact, yeah, group is predicting your accountability ratings. So that's how it works. You can do a paired samples t-test. So for instance, we can look in the support data. We have measures for people's ACT reading scores and their ACT math scores that are on the same scale and they're nationally standardized. So perhaps it makes sense to compare them to each other. So we can look really quickly. We can say what, well, let me zoom. It's kind of hard on this small screen here. This is like what it's like to work on a netbook. So we can take a summary of ACT reading scores, and we can say, okay, there we go. Now, a lot of people didn't take the ACT. In this data set, we have SAT scores as well. So we're not getting everybody here. This is maybe not the best true hypothesis test. And then ACT math scores. We can see that the means are different. And I don't know why it's showing me, I don't know its rules for decimal places, but the means are not whole numbers. But it chose to show me whole numbers here. But it rounded off to whole numbers. Anyway, we can take a quick look there, and then we can just do a t-test. And I wanted to show off one or two different functions of the t-test function, or two different features of it. So we do t.test again, and we can do these two things, not the formula interface, because the data is organized so that one entire column will be a person's reading score and another entire column will be the person's math score. Now you can rearrange the data into long format, and you could use the formula function. But for paired samples, it's most likely that it's going to be like this, so you can just do variable and variable. So one column from the data set and another column from the data set. Now this tells it to do a paired samples t-test. And this tells it to do a one-tailed test. You don't have to do this, of course. But let's say our hypothesis is that UTPA students do better on their reading scores than on their math scores, because these were social science students. And I make jokes to my students. Actually, I only did this once, and I felt bad about it, so I've never done it before. Somebody was nervous in my stats class. I said, but I'm really worried about the math or something. I said, don't worry. Nobody thinks psychology students can do math. If you could do math, you'd be majoring in engineering and making your parents proud right now. So they laughed, and it was a little too nervous, the laughter that they had. But there's something to be said for that. If you're majoring in psychology, you probably didn't get nearly the math training that somebody who's majoring in engineering got. So you probably got a lot of verbal learning training, lots of verbal learning. So let's say we think that students in the social sciences, which is where this entire sample came from. It was all psychology and other social sciences. They're better at reading than they are at math. So I don't know why there's a space there, but I don't want it there. Doesn't matter. But so alternative equals greater. That alternative equals, you can either say greater or less. And if you leave nothing there, then it'll be two-tailed.
H1 means the null hypothesis, right?
Excuse me?
H1, it means the null hypothesis.
H1 is, the way I'm putting it here, it's an alternative hypothesis. H0 is usually the null. Yeah. So in this, if you say greater, greater means whichever variable R comes into first is assumed to be greater than whichever group R encounters first is assumed to have a greater mean than the mean of the group it encounters second. So since I've put reading first in the t-test function there, then the hypothesis is that reading should have a higher mean, that there should be a higher mean score than, there we go, than a math score. So here we see, again, all the same stuff, the t-score, the degrees of freedom, which, again, strangely turned into a round number, which doesn't happen that often. A small p-value, definitely less than 0.01, 0.001, so we reject the null hypothesis. Alternative true difference in means is greater than 0. Greater when you take mean 1 minus mean 2. So over here, mean 1 is ACT reading score, mean 2 is ACT math score. The order matters when you're doing a one-tailed hypothesis test. And often I get it wrong the first time and the results don't make any sense, so I have to go back and reverse it or say less instead of greater or something. This is not going to show you the means, so that's why I did the summary up here. So this won't show you the means, it'll just show you the mean difference. And it'll show you the confidence interval. Interestingly, when you do a one-tailed hypothesis test, it gives you a one-sided confidence interval, which is not something I've encountered very much. I think it's technically correct, but my stats teachers never bothered to show me that. But I think it's neat. Infinity, and if it was a negative test, if it was alternative equals less, it would be negative infinity. And infinity and negative infinity are actually number representations. They're specialized number representations in R. Sometimes if you get an error, it'll say the answer is negative inf or positive inf, especially if you use the max and min functions. Something about the way they run, if you do something wrong and give them missing values or something, they will give you a positive or negative infinity as a result. So anyway, the mean of the differences is 0.89 points, which isn't very many points, ACT points, because ACT goes from like it's 5 up to 30 or something like that. It's somewhere in that range. So less than 1 point. But we have a lot of people, and the differences were fairly consistent. So we reject the null hypothesis and say, yes, social science students in general have higher reading scores than math scores on the ACT, at least those who took the ACT in my study. Questions on t-tests and how we run those? Maybe we have a chance for regression and ANOVA before we go. Those are quicker and easier than you might think, as long as you understand what you're doing. Now, R is something that is harder to do anything with if you don't understand the basic stats. And unfortunately, if you don't understand some things about how to work with command line interfaces like this. And the R people are very proud of this. I think it's maybe a mistake on their part. It's a little bit of an elitism in the R community. They're very proud of the fact that you can't make it work if you don't understand a lot of things first about statistics. So if you look at the message boards, there's a lot of, obviously, what you're seeing here is an error because you failed to consider blah, 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 blah. Oh, there's some mean answers. These days, there's been a strong push to have nicer answers when people ask for help with R, so I think that the answers are nicer in the last few years. But some of them, they're just so proud of the fact that that ignorance punishes you. All right, let's do regression first, because ANOVA in R is done after first doing a regression analysis. You do regression first, and then you run a separate function on the results of that to get your analysis of variance. So let's install this package, the psych package, because it has, I've already got it, so I don't need to. So do that, install packages psych, and then library psych. So install packages will download from the internet this bunch of functions that's called psych. I think it's created by a guy in the psychology department at McMaster University. A lot of R stuff happens with 2 or 3 people at McMaster who are extremely active. I think one of them's in political science or economics, and then the other one's in psychology. Anyway, and then library psych pulls them all into memory so that you can use the functions. And I just want them for one specific function, which is just kind of neat, that can show you a bunch of correlations all together. So this function, it's called pairs panels. This function here, pairs.panels, it needs a matrix or a data frame with a bunch of variables, so we have to give it one. But we don't want to give it our entire data set. So let's look in the support data set, but you saw that it has like 100 variables, and so you don't want to just do a correlation matrix of 100 variables times 100 variables. That would be crazy. So let's use this function called subset. Subset is really nice. It gives you a subset of a data frame. So we can create a new data frame, df.reg, so like regression data frame. Subset of the support data frame, that's the first argument, support, comma, select equals, and then you have a C, and in between the C, you just put the names of the variables you want to select. So it'll create a new data frame with just the variables that are listed between those C's. And you don't have to put them in quotation marks, which I know is a cheap reason to love that function, but it's one of the reasons I love it, because I get tired of putting things in quotation marks all the time. So if you run this, you create a new data frame, and then you can just do pairs panels on that data frame. You don't have to. You can specify within pairs panels, oh, select this column, okay, select this column, and it's a little fussy. So it's easier to just do this. Now it's going to need some space, so you guys will probably have no problem on your larger screens, but there we go. So this is a nice function if you want to just see the intercorrelations and patterns of intercorrelations between some variables. It's really nice. So it shows you on the diagonals the histograms of the variables. I'm just going to pretend like these aren't horribly skewed for right now. So I probably should not do regression with like this and this and this. These are horrible. These are probably violating all sorts of assumptions because the normality of these things is so questionable that I can't imagine the residuals are going to be terribly normally distributed. And we'll check that in a minute. But let's pretend they were all normally distributed, like this one. You can see the intercorrelations. You can say, oh, okay, yeah, there's some intercorrelations here that are interesting. What I'm interested in is predicting a student's self-esteem based on these other 6 predictors, or 5 predictors. So predicting a person's self-reported level of self-esteem on the Rosenberg self-esteem scale. So this is just a quick way to see, okay, that's my intercorrelation pattern there. It also tells you if you violated assumptions, which I have, but we're going to ignore that for a minute. We're going to be very bad statisticians for a minute and ignore that. And now we run the regression function, but you don't want to just run this function. You want, as is so often the case, you want to create a new object and assign the output of this function to that object. So I created an object called rse.mod. So Rosenberg self-esteem model. And the function you use is LM, which means linear model. We use that for lots and lots of things. It can do lots of stuff. And then we use that formula interface. So we're going to have the formula here, and we're just going to type in the names of the variables, and then we're going to say data equals and tell it which data frame those variables are in. Some functions have this data argument. It's really nice. Other functions don't, but LM does. So we can say Rosenberg self-esteem score predicted by emotional intimacy with your mother score, so self-reported emotional intimacy with your mother, emotional intimacy with your father, positive academic support from your family, negative, we call it anti-support from your family, and perceived stress. These are all questionnaires that the students filled out. So you do Control-Enter and nothing happens, and it happens very quickly. But we created this new object. We created rse.mod. Now if we take the summary of that, we have our regression results. Here, let me give myself some more space here. So the summary of that gives us our regression results. It shows you what your formula was, what went into that. Gives you a quick rundown of the residuals. They're relatively evenly distributed anyway. They only go down to -15 and +11. It's not horribly skewed residuals, at least on first glance. It included an intercept. There's a way to build a model without an intercept if you want it. You can do lots of things. And then it shows you the the regression coefficients, the B values for each of these predictors. And it shows you whether each of them is significant. So we can see that emotional intimacy with your father is uniquely important in predicting your self-esteem, whereas emotional intimacy with your mother, that's only marginally significant, P of 0.08. That's not a statistically significant predictor. This is a stronger predictor, 0.16, 0.10. And positive support from your family was not a predictor, but there was a statistically significant negative prediction for anti-support, for your family refusing to support your college career, saying bad things like you shouldn't go to college and you're too dumb and things like that. That's what was in this questionnaire. And then positive, the perceived stress scale. This was a very strong predictor compared to the others. And this had a strong negative B-value. For every 1 point increase in the perceived stress score, we expect about a third of a point decrease in the Rosenberg self-esteem scale. And that's statistically significant. We can see multiple R squared is 0.29, which is actually pretty reasonable. 30% of the variability in Rosenberg self-esteem scores is accounted for by the combination of these things. So maybe I should just report this. This is actually kind of nice. Maybe I should just publish this. This is good, you guys. I'm predicting Hispanic college students' self-esteem. I can get published in a journal. All right. Anyway, if we want to see how badly we violated our assumptions. Yes, acknowledgments to all of these people. So plot normally just makes a scatter plot or something, but when you plot the results of a linear model object of a regression object, it shows you diagnostic plots, which is kind of nice. So you do Control Enter and you see hit return to see next plot. So you have to click over here and hit Enter. How nice. So it shows you a residuals plot. So fitted values versus residuals. And you can see there's kind of a problem. We've got a constant variability problem there. There's very low variability on the right, pretty high on the left. Yeah. I'm going to have to deal with this before I try and publish this data, because that's a big problem. The next one it shows you is a QQ plot of the residuals, which is nice, and we can see that mine are negatively skewed. So that's kind of a nice little diagnostic plot too. And then the next two are trying to show you influential items, influential observations, and it even labels the most extreme of the influential. So the square root of the standardized residuals by the fitted values is 1. And it puts a low S curve through the middle so you can see sort of what the natural line of things is. And this is bad. This suggests that there's a nonlinear relationship happening somehow. So I should investigate this more. I don't know what that would be, but I should investigate this more before I try and publish this. And then finally we can get residuals versus a measure of leverage. So I think this is Cook's distance? Oh no, Cook's distance is this weird envelope. I don't understand this terribly well, except to know that if you have a dot way up here, you should really try running your model again without that dot because it's heavily influential on your model. So that's regression. And regression is super easy to do because you just do LM, Y, tilde, x1 plus x2 plus x3. Really nice. And then you do a summary of the results. Now, we can look at the residuals because the regression object is actually a list of many, many different collections of numbers. So, for instance, I guess we're out of time, so maybe we won't do ANOVA today, unless you guys want to stay another couple minutes. So if I do RSE.mod, and I just type it, all it's really going to show me is the coefficients, just the regression coefficients. But don't let that fool you into thinking that's all that's in that object. That is an incredibly complex object. So what if I type, what are the names of RSE.mod? Oh my goodness. Each of these is another little object like packaged together, and one of these is residuals. So I can type RSE.mod, and it's a list, just like a data frame. So I can say $, show me the residuals. There we go. Well, so I'll go over here. What's a summary of the residuals? Okay, that was actually in the regression output. A 5-number summary of the residuals. What if I want to see a histogram of the residuals and see how normal they look? There we go. Now we can see from that QQ plot what it was doing. They're negatively skewed. I could do a QQ plot of the residuals myself, which is what they just showed us in the diagnostic plots. I can standardize the residuals because there's a function called scale that just turns anything into a z-score. So I can do histogram of scale of the residuals. And that'll just give me the same thing, but now z-scores. And that's more useful to me because I have a hard time thinking of, what's the scale of this questionnaire? Is 15 big or not? I don't even know. But -3 z-score, I know how big that is or how big that isn't. That's a little concerning to me. If we have residuals that are a z-score of lower than -3, then maybe I know I should be concerned. Okay, so Would you like to wrap up now, or would you like to do ANOVA for the next 5 minutes or so? I can go either way. You want to stay? Does Sophie speak for you? Okay. You are all under her power, obviously. All right, so let's do ANOVA. Now, ANOVA, you just do an LM, a regression analysis, but your predictors are qualitative. Your predictors are categorical variables. So from the punishment data set, let me just do, you can always look and see what your values are by using the table function. So table pun $treatment.pro. There's only two values here. Treatment professional only has two possibilities. This is a categorical variable. You can be a no or you can be a yes. That's all. So I can use a table function just to see what my values are, and I do that frequently. And dev level. People saw different questionnaires, and the offenders in the questionnaires were randomly assigned to have different ages. And so I grouped those ages into developmental levels. And I'll show you that here. So we can do table of punishment dev level. So I grouped those later into whether the offender in the hypothetical scenario in a person's questionnaire was a child or a teenager or an adult, an adolescent or an adult. So this only has three values. So if I do a factorial analysis of variance with those two predictors, it will be a 2x3 analysis of variance. And it'll actually be kind of mixed there. No, it won't. It will be between subjects. It's all between subjects. Sorry. Some of the factors in this study are actually within subjects, repeated measures, but these are not. These are between subjects, as you can see from the tables. So we just create a new object. So I'm going to call it punishment model, pun model, LM. And this time, I want to see if people's punishment ratings towards offenders were affected by the developmental level of the offender they saw, and if they were affected by whether the person was a treatment professional or not, whether they were a student or a treatment professional. And I'm going to use the punishment data set. So this is the same as before. I hit Control Enter, and now I have this new object. It doesn't show me very much if I just type in the name of the object. It shows me regression coefficients. So what it did automatically is a regression analysis, taking those categorical variables and creating the appropriate number of numerical dummy-coded vectors, and you can change the rules that it uses for those dummy-coded vectors, and it did a regression analysis there. And if you give categorical variables to R to do regression, it does very reasonable regression. It creates the right number of dummy-coded vectors for each categorical variable, and then it clumps them back together. So you can see you have developmental level 2 teen and developmental level 3 adult. So developmental level this level versus 1, and this level versus 1, and treatment professional yes versus no. But we don't necessarily want that. We can do a summary if you want to see the whole regression output. We can do here. There we go. We can do a summary of the object, and this will show us if we were running this as regression, but we probably wanted to run it as ANOVA. So what we do is we do a second step. We ignore all this stuff, and we use one of the many ANOVA functions. Now, you might be tempted to do AOV, but my understanding is that AOV does a more of like a regression ANOVA. So if you do AOV of this object, which stands for analysis of variance, then it's just going to show, well, I'm sorry. Oh. I was wrong about that. I was in too much of a hurry when I did this. It just arranges things a little oddly. It's not arranged the way an ANOVA table is usually arranged. So it's transposed. Usually have sum of squares and degrees of freedom in columns, but they're in rows here. So it shows you the sum of squares of offender developmental level, sum of squares of treatment pro, and the sum of squares error, sum of squares of the residuals. And it's not showing you any of your summary things, but I don't really care because I don't use this very much. It uses type 3 sum of squares by default, and I want a little more control. There's a different function you can use, which is called ANOVA. If you do the same thing, ANOVA of punishment.mod, it will give you a table that looks a little more familiar, and it will give you p-values, which is kind of nice, because most of the time where I publish, people want p-values for your effects. Can anybody notice anything that's missing there? for a factorial ANOVA? There's a line missing. There's a line missing, not technically. Statistically speaking, this is perfectly fine, but there was a very specific decision that was made by the analysis, and by me actually, by default. There's no interaction term. And in analysis of variance, it's just, I think because of the history of the fields that have used analysis of variance, they always do the interaction terms. In regression, you don't. So when I did this up here with a plus, it didn't do the interaction terms. So I can change that to a star, which is times, and that will do each individual effect, and it'll do the interaction between them as well. So I'm going to rerun that, and then I'm going to go down here to ANOVA again. And now we should see an interaction term. There we go. And it's going to show it with a colon. I don't know why it's a colon instead of an X. Maybe an X could be confused for being another variable. The interaction is non-significant. But the effective developmental level is a strong effect, and the effective treatment professional is a strong effect as well. Now there's another function, and it's in the CAR package. CAR stands for Companion to Applied Regression, which is a textbook that has an R package that goes with it. So if you install that package and load the library, it has a function called ANOVA with a capital A, and that allows you to choose your types of sum of squares. You can choose type 1, type 2, type 3, or I think even maybe type 4. And so I did over here ANOVA with a capital A after I loaded in those functions. I did it on this object, but then you can tell it which type of sum of squares. I chose type 2 sum of squares, which is more reasonable if there is an interaction, right? Because it makes better choices about the marginal. This is a very unbalanced design. If your design is perfectly balanced with the ends and all the cells, you don't need to worry about this, but this is an unbalanced design. So we look down here. The p-values look pretty much the same, but the sum of squares are a little different. 46.7, 45.5. Actually, that's the only different one. Everything else looks about the same. But sometimes it can be the difference between significance and non-significance, which one you choose. And so there's a really important decision to be made there. All right, well, I think I'm going to wrap up because we've been here longer than anybody wanted to, and I'm supposed to go to a department meeting right now. But are there any questions before we go? You have the file, and it has even more stuff in it. I didn't get around to doing the chi-square, the logistic regression examples in the file. Sorry about that. I was in too much of a hurry, but we didn't have time for them anyway. Does anybody have questions? Excuse me, what was it? Oh. Let's go back to the plots here. Oh, here we go. The fact, how did I know that they were skewed? The fact that these droop down on both ends down to below the line suggests that it's a negative skew. And then when you look at the histogram of them, you can see there is a negative skew there. So that's played out in the... I'm not the greatest at understanding QQ plots. I have some quick rules of thumb. If both of the lines droop down to below the diagonal, then it's negatively skewed. If they both go above the diagonal, it's positively skewed. If it's like an S or a Z shape, one of them indicates heavy tails and the other one indicates thin tails, I think, compared to normal. But I can't remember which is which. I always look at a histogram and a QQ at the same time.
Yeah, if the positive side goes up and negative side goes down, that's heavy tail.
Okay. I always look at them both at the histogram and the QQ anyway, because I have a hard time remembering, except for those two quick rules about the QQ. If they both go down, it's negative, and if they both go up, it's positive.
But to my eyes, that's different versus this is pretty much normal. Look at a QQ compared to this, it's close to normal.
Well, and if you consider what's happening here, we're testing against the sampling distribution, not against the sample distribution. We're testing against the sampling distribution of all possible differences between the variances, and that will normalize itself. So with t-tests, for instance, if you've got a sample size of greater than a couple hundred, even if you have really extreme skew, it's probably okay to go ahead and do it because the sampling distribution of those means is extremely normal.
Exactly, and the t-tests, both t-tests and normal, very robust to the non-varieties.
Yeah.
Very
Although I have read stuff recently that tells me that I'm wrong about that. That's what I've been saying for years. But I've read stuff recently that suggests that traditional parametric methods are not as robust as we think they are. So more stuff I've got to dig into. But luckily, R has lots and lots of alternative modern methods that don't rely on traditional parametrics. That's just more to read.
Well, I think the criticism from the non-parametrics, they really try to challenge the traditional methods. But for saying it is robust, because like you said, when the sample size is large, we agree that the assumption, the assumption is the sampling distribution of sample means instead of original distribution.
Right, but the stuff I was reading, a colleague of mine sent me an article that was about modern methods and why you should use them over traditional ANOVA and t-test. And it was skipping past those questions. Much of the research was skipping past the questions of theoretically what's happening and just doing simulation studies and finding out how often are you wrong, how often do you make type 1 errors, type 2 errors, compared to how often do you think you're making type 1 and type 2 errors. And some of those are disturbing. Some of those show that we're making more errors than we think we are, so that's not good. But the recommendation is not to use non-parametric methods. It's to use modern modifications of the parametric methods in most cases. Like, for instance, ANOVA using trimmed means and, what is it called? Somethingized variances.
Yes, weighted.
The something variances that...
Weighted version of ANOVA.
Yeah, some kinds of weighted versions too. Anyway, I'm all finished, and I have to go to a meeting. So thank you for coming to class. Lots of fun. And I'll put this stuff on Tegrity maybe after editing it heavily. Bye-bye, everybody.